notation. And for a model to compare to, we can think of electrons as money. And curved arrow notation basically shows the transfer of money or electrons from one chemical species to another. In this model, we can see that the person who has more money will be giving money to the person who has less money. The person with more money in chemistry is called the nucleophile, while the person with less money is called the electrophile. And in this model, we can see that sometimes people are going to be sources, but sometimes they're going to be destinations. And this is because sometimes if you have one person with $10, that person could be considered rich compared to a person who only has 1 cent. But if you take that same person with $10 and compare it to someone with $100, that person becomes poor. So we can see that whether a chemical species is an electrophile or a nucleophile depends on what it's being reacted with. Next, to go into more of the chemistry behind it, we see that the nucleophile, represented here, has very high electron density, meaning it either has lone pairs or a negative charge. And the electrons are transferred over here to the electrophile, which either has a positive charge or is attached to something extremely negative, electronegative, for example, a fluorine. The arrow always flows from the nucleophile to the electrophile, and it cannot go the opposite way. Some examples of nucleophiles, or nucleus lovers, are iodide ions, ammonia, and hydroxide ions. This is because they either have negative charges or have lots of lone pairs. Then electrophiles, examples of them include carbocations, hydrogen ions, and AlC3. These all either have positive charges or are attached to something extremely electronegative. In this example we see here of curved arrow notation, this arrow shows the transfer of one pair of electrons from the F- ion to the Bf3. The F- in this situation is acting as the nucleophile, while the Bf3 is the electrophile. After one pair of electrons is transferred over, it becomes Bf4-. We can see that this minus is carried over to the entire molecule. In this next example, we see a ketone molecule. And this shows that sometimes a molecule can be a nucleophile or electrophile depending on the situation. For example, this ketone is a nucleophile when it's reacted with H+, and this same ketone is an electrophile when it's reacted with OH-, because the OH- and the H+ have differing charges. This O is negatively charged, so the carbon attached to it is delta positive or partially positive. The O is negatively charged though, so that could make it more like a nucleophile. This is especially common in organic molecules. Next, we see that the tail of the arrow goes to the head of the arrow, which is the destination. And another name for this is the electron donor and the electron acceptor. The bond can be broken or a bond can be made. And when this bond goes to another bond, it's also called bond movement. When a bond is formed, it's known as bond creation, and when a bond is broken, it's known as bond breaking. So these names are pretty much indicative of what the process is. We can see down here that the arrow can either have a full head or a half head or fish hook. This arrow represents that only one single electron is moved instead of a pair of electrons as more usually is shown. And we'll get more into this in the next slide, but I also want to mention that the bond broken or formed or moved can be either a sigma bond or a pi bond. So that means it could be either one of the single bonds or double or triple bonds. And here we can see that heterolysis describes the reaction if both electrons in this bond go to one of the elements or the compounds. And this compound or element is going to be the more electronegative one because it can better accept the electrons. However, in homolysis, we use the single barbed arrow, and that shows that one electron is going to each. For this homolytic bond cleavage, we see that curved arrow notation can also be used to represent bond breaking and forming two separate products from one single one. So both of the electrons in this bond are going to the Br minus, creating a negative ion with a positively charged compound over here. So since the only major application for curved arrow notation is that it's used in chemistry to show electron transfer and predict products, I'm going to give 4 examples of varying difficulty using the curved arrow notation. In this first example reaction between a cyanide ion and a bromine compound, the cyanide ion acts as the nucleophile, while the bromine compound is the electrophile. After the electrons are transferred over, the Cn- becomes a cyanide compound, and the bromine is split off from this carbon because it can only have 4 bonds. That's a relatively simple example. In this next example, we have a set of 2 arrows to show 2 different pairs of electrons being transferred. One from the oxygen to the hydrogen and the other from the bond between hydrogen and oxygen to the oxygen. This results in the breaking of a bond between the oxygen and hydrogen to create water as a byproduct, and the addition of the extra hydrogen to the ketone molecule. For this third example, we have homolytic bond cleavage between the 2 bromine and Br2, creating 2 Br. And one electron in this bond goes to the bromine and the other goes to the other bromine. So this is why we use the single barbed arrows. And in this last example, which is quite complicated looking, we see that curved arrow notation can be used to predict products even if you don't know what they really are. Like, for example, we haven't really learned what this compound is called. But since we can identify that this is the nucleophile because it's attached to an extremely positive element, and this is the electrophile because it's attached to extremely electronegative element, or bromine, we see that a bond forms between here and here. And the Na and Br have to be cleaved off and form a separate product of their own because carbon can only have 4 bonds. We see in this example that we don't need to know the specific reactants in order to predict the product, as long as we can identify the nucleophile and the electrophile. So that's it for today, and I hope you learned something about curved arrow notation.